Good afternoon. The slide is visible.
Yes, sir.
Okay.
So we were discussing about classification, and what we uh, started about that classification is classification using logistic regression.
Excuse me, sir.
Yes.
Sir, in the previous class, you mentioned in the loss slide function, there was a slide on loss function in which it was written that we choose the hypothesis class once the machine learning algorithm is designed, right? So, what is hypothesis class? That was not very clear. So could you explain it?
Yeah, hypothesis class, what we have discussed so far, actually the concept of hypothesis class is basically given in a very concise way in last class. So the elaborative thing will come later, but for your question answer, I just said what actually it is. Let me go to there. Yes. Here, what we have shown that when we are going to, what is actual problem in a supervised setting, what is given a set of training example. Set of training example is given. So what does this geometrically mean? Geometrically mean, let it is an example is two-dimensional. So these are the means is some kind of these values. Okay. So now what is required? That we have to model, we have to find out a function that we said that hypothesis function. And this hypothesis function is going to, we are going to devise a hypothesis function. Okay, something like that. Now, your question is, I said that first we select the type of machine learning algorithm. You see the type of machine learning algorithm here.
Yes, sir.
That we think appropriate for this particular learning problem. Now, given this kind of problem, that so we say that we are going to kind of curve fitting problem. So the problem is basically that the model is basically try to find out a function that is maybe linear or nonlinear. So it's a kind of curve fitting problem. Okay. And with this curve fitting problem, so if we say our function is linear. So this is a kind of constraint or assumption, you can say. It's the same thing, constant or assumption. That we assume we find a curve which is linear for this particular problem. Now, this may be anything. This may be neural net. This may be SVM. This may be anything. But we said that, okay, no, we are a kind of a curve fitting. So we are trying to find out a curve out of there. And this curve is supposed to linear. So this is our assumption or constant, whatever you want to say. So what we are doing. So for this particular problem, this defines a hypothesis class H. So what kind of problem we are defining? We are basically a curve fitting. So this hypothesis class is this. Okay. H in the set of function so this hypothesis class is a set of hypothesis function. So what is a set? How we define the set? We are going to define the set such a way that is a curve. Again, curve, this assumption is linear. So this is the linear means straight line here. So it's in the 2-dimensional. If it is a 3-dimensional, it may be a linear hyperplane. Okay. So this H is a set of hypothesis function. Those are linear or those are straight lines here for this particular problem. Okay. Now this straight line, there may be any straight line. There may be any straight line. So there's a set of these straight lines. So that's why whatever your function, hypothesis function, H is belongs to this class. So this class is all straight lines here under this assumption. Is a curve and this curve is linear in nature. Getting my point? What is hypothesis class?
Okay, sir. So this entire class can be generalized by suppose saying g of theta naught plus theta 1 x plus theta 2 x2. Can we say that entire like as we vary theta naught, theta 1 and theta 2, I can generate the entire hypothesis class. Is that the case?
That defines the hypothesis class is basically, if you say it's a straight line, then what is this straight line means what? Mx plus c, sorry, c, mx plus c. So m is if you do theta 1 and it is theta 0. So then this hypothesis class is basically 2 parameters of there. Theta 0, theta 1.
Okay. So as we vary the parameters, we'll get the entire hypothesis class, right?
Yes.
Okay.
Yeah.
Okay, I
So,
got it. Thank you, sir.
so but this is a kind of example by which I define. Will come up again the theoretical assumption of what is hypothesis class, how all this. There is some theoretical there is a called that one or two class I will take in after 1 week or something that define, then you understand everything. There is some mathematical things more precisely you can understand, but for now it is the we are doing in this way.
Oh, okay, sir. Thank
Same
you.
thing, but we will get it. So now what is what we are basically doing here, that we are using a logistic regression. Now what is logistic regression? We defined logistic regression in this way. Initially our hypothesis function is theta is theta transpose t, something like that. As you recall, I think go to this slide. Yes. Linear regression, our hypothesis function is this. H theta transpose. H x theta is equal to transpose t. And what we said, that when we define a logistic regression, that we put a G over this theta transpose t. And what is this G? G is basically G of Z is defined in this way, 1 by 1 to the power e to the power minus G. And we say this is logistic function, logistic or sigmoidal function. So this is basically definition of the logistic regression. That I think you should remember it. Remember here. So here we're going to find out the associated cost function for this logistic function. So what is our logistic function? Is basically h theta transpose x. H theta x is 1 by 1 plus e to the power minus theta transpose. So this is our logistic function, where our training set is something like that: x1 a1. This is a paired training set, and up to the number of, so training samples, number of training samples to m. So m examples here, m example you can see. Now question is how to choose this parameter theta, because you know this is theta, so theta transpose x. Okay, so that is the parameter theta. So that this is the question. So here you say that in linear regression, how we measure the cost function? I think that is our h theta xi. This is our predicted. Let's say in this way, minus what is the actual value yi, and we take the square root of this, and we sum it up over I is equal to 1 to m. So m number of data sample, and we normalize 1 by 2m. So that was our cost function. So here you just write same thing. Okay. So we rewrite this function, this statement. We rewrite this statement in this way: cost of h theta xy yy. So h theta xi, that is your predicted value. So this is your predicted. This is actual. The difference between these two is actually this. You take a square root of and take a square root and take a kind of, since it is a single instance, we take 1 by 2. If it is there is a this some summation term is not there, it's a single instance. Okay. So j theta is basically 1 by m, I is equal to theta of xi by I. So this is basically, that's why we define in this way. And where is h theta? H theta is this in this definition. Now it's just a rewrite of this. Okay, nothing more. Now see what happens. Now the problem is that we have C that I think you can recall again. I go back to this function. Wrong back. What we have discussed here. You see that this is the, for linear regression, the cost function if you put is a convex in nature. So since it is a convex, then the, what is the thing? The local minima more or less the global minima. Okay, you understand that what is the useful of convexity? So that we have studied very elaboratively. But here you can see, since you put this g theta, this j theta, basically now this cost function, that what we have defined here, that cost of h theta xi yi, that cost of x theta I and yi, this function is non-convex. and something like that. Now you can see if you are stuck here, sometimes just here, it is very tough to get back, because you can say this is also a kind of convex kind of thing. If you trap here, you cannot get here. So this is the problem of logistic regression, that the cost function, due to this logistic function, okay, logistic function, that why it is so, because of that our h theta x is what, 1 by 1 plus e to the power minus theta transpose x, due to this exponential function. Okay? If we just do this kind of squared sum, this will happen. So what we can do to get rid of this problem? So we do one thing, we change the cost function. Earlier it was, the cost function was that, the cost function is just a squared sum. So that was x h theta xi minus yi square root summation 1 to I is equal to 1 to m and 1 by 2m. That was the first function for linear regression. But now what we'll do, we now you see this is our cost of h theta xy. Now we write in a different way. Now we write when y is equal to 1. Okay. Then we write our cost function is minus log of h theta x. Okay. And when it is 0, that means y is equal to 1, we have to predict our h theta of xi as 1. That is our requirement, because it is 1. And y is equal to 0, we have to predict h theta of xi is equal to 0. That is y is equal to 0. So if it is 1, then our cost function is minus log of h theta x. And if it is 0, that we supposed to get this 0, we get it is a log 1 minus h theta x, if it's equal to 0. Okay. So what is basically that means? That means that look at this curve. Okay. So if you see that if h theta, this curve is basically a log of h theta x, this curve, this. Okay, kind of log x. Okay. Now what happened? Now you see that this is minus log of x. So now what is important here, you can understand that if this is h theta of x, now what is required? This particular curve, it is cost is 0. So cost is basically 0. If y is equal to 1, then h of theta x is equal to 1. So what does this mean? That if you know that the level is 1, okay, so what you want to do, your prediction, h theta is your prediction. If your prediction is also 1, so what you required, what you intended, that if the class level, actual class level is 1, the predicted class level should be 1. This is your intention. And if this happened, then the loss or cost, whatever you say, is close to 0. Okay. So here you can see that if h theta x, if y is equal to, this is y is equal to 1, this is this assumption. If y is equal to 1, this h theta x, if it is this h theta x close to 1, this h theta is, then the cost will go to, going to what? It is downgraded to 0. So this is cost 0. So in this is the cost 0. So it is 1. So exactly this thing here. If you not understand, please ask. I will repeat the thing. When class is 1, what should our classifier do? That the prediction should be 1. If we are happy, then because it is the correct prediction, then the corresponding cost is very close to very less cost. But the other hand, if h theta x is 0, if it is going here, going to here, okay, so that means, but it is y is equal to 1. So you can say y is equal to 1 means what? This, let's say this is apple. Okay. But your h theta x say, no, it's a non-apple. Something like that. Then this is a misclassification. This is a right classification. It's a right classification. But if y is equal to 1, but our h theta x saying it is 0, then it's a misclassification. Then our cost is very high. Cost should be very high because we don't want to input more penalty, and so it's infinity. So here exactly. But as h theta greater than is tends to 0, cost going to infinity. Okay. So that part only, this particular equation we are saying. Okay. When y is equal to 1. So this captures intuition that if h theta is equal to 0, predict y is equal to 1. This is given. Or x, what is the probability that we can say that is equal to 0, but y is equal to 1, we will penalize the learning algorithm by a very large cost. Okay. So this thing, this is basically what our intended thing. Now please ask if anybody can't understand. Okay, very good. Now come to this part. This part. When y is equal to 0. So this curve is for what? This is minus log 1 minus x. This is this curve. Okay. Now ideal what is? Now the situation is reverse. Now y is equal to 0. It's a non-apple. This is actually non-apple. And y is equal to 0 if, now if we say our h theta x, if we want to correctly classify, it should be very close to 0. And if it is so, then we what said? Our cost is very close to 0 because this is the correct classification. Okay. But if say our h theta x is equal to greater to 1, but you please remember this is 0, but we are doing a wrong prediction. So this is a wrong prediction. So what penalty? But cost will be very high. So cost will be tends to infinity. Same logic. So this caption is this exactly happened. Now you see here y is equal to 0. Now h theta x is if it is equal to greater than 0. So it is if you go to 0, the cost is very close to 0. On the other hand, if it is goes to 1, that is a misclassification. This is the correct classification. It's a correct. And this is a miss. So the cost is very going to infinity. To infinity. Okay. So this thing, the capture intuition that s theta is equal to 1, you predict this is equal to 1, but y is equal to 0, will penalize the learning algorithm a very large cost. So now we understand that this is also what for our cost function. I am not going to discuss in a very statistical thing. Will sometimes if time we'll say this way of toss is basically the is called maximum likelihood estimation kind. So this kind of thing we used there. The way of define how we define this cost function. It's very analogical or very kind of that might that's likelihood estimation. This is the likelihood, and by this way. So I'm not going in that way, but this is the very those who know the statistics very well. It is basically that thing. So the thing is that it can be shown that the overall cost function is convex function and local optimum is free. Now you can see if you adjoin these two functions, this is become a convex. But details of such convexity analysis, but how we reach this convexity, that beyond the scope of this course, so we are not going to discuss here. But in general, if we define in this way, our this noise or cost function to somewhat become convex. So this is the basic idea of cost function for logistic regression. Now this function is looking so complicated. Complicated means it's very it's not that much mathematically you can so handy. So what we are going to see that this is our linear regression. Cost function. This is our logistic regression cost function. Now we rewrite this logistic regression in this way that this is the cost of h theta of x, y, whatever we have said. Now, what is that? This is when y is equal to 1, that this. So we put minus y log of h theta x, and we put minus 1 minus y log of 1 minus h theta x, exactly this. Okay. Now you see, when y is equal to 1, this particular thing, then y is equal to 1 minus what? This 1 minus 1, 0. So this part is become 0. So it become cost of this minus log of h theta x because y is equal to 1. Because y is equal to 1. Okay. And if y is equal to 0, then what will be? If it is 0, so this part will be 0. So it's a minus 1. So minus here. And log of 1 minus h theta x. And y is equal to 0. Since y is equal to, this is y is equal to 0. So this part in this case is equal to 0. So it is minus log of 1 minus h theta x. because y is equal to 0, so y, so minus is there. So ultimately, if we write this, we actually, in this sense, we're writing this. Okay. So our cost function of logistic regression is this in mathematical way, if you write it. Okay. Now, if it is a cost function, so how we get the minimum of this cost that we are trying to do? Now, our j theta is this cost of h theta x of I and yi. Now, what is cost of x h theta xi yi? We put yi into log of h theta xi plus 1 by yi log of 1 minus h theta xi. As this is what we have defined here in this function. We just rewrite this function, and what is we sum it up over m is number of samples, number of training samples, okay. M is the number of training samples, and this is the normalized by 1 by n. So if we exactly do this particular, we can get this function, that 1 minus m by yi log h theta x I plus 1 minus y of I log of 1 minus h theta x. So this, as I said, this is coming from maximum principle of maximum likelihood estimation. Okay, so that is the well-known result of the statistic. So now what we want to do? We have this j theta. What we have did the minimum of j theta, because that is our idea, because it's a cost function. And what we have to make the cost function is minimum. That is the same logic. So we obtain, we have to minimum of theta or mean or j theta, and we have to find such theta so that we can make this j theta minimum. That is the thing. And here we are right basically this, that for y is equal to 1, that for this y is equal to 1, what will be the probability of x given parameterized with theta? And this is your hypothesis function. Okay. Now, at least we can understand that what is our problem is turns into this fact. Now we have to find the how to get theta to minimize this j theta. So question now, how to minimize j theta? That is the main question. Now definitely we put our GD, that means gradient descent algorithm, over that. Now we repeat this. This is our objective function j theta, and where we have to minimize this for theta. We find out j theta. That is our goal. We use gradient descent. And what is j theta? It is what minimum j theta. Repeat j theta. So what will be the this what we have done before? J theta is equal to theta j is equal to theta j minus. This is our what this uh, this what is alpha, the this anybody?
Learning rate.
Very good, learning rate. And this del of del j theta and j theta. So this thing we have to do. We have to differentiate of j theta with respect to theta j with this j of theta. That we have to do. And then simultaneously update for all j thetas. Okay. So theta is the vector. That means that means theta 0, theta 1, theta k or theta n, whatever this vector. So that we have. Now you just take, so this is basically the differentiation of this j theta, because that part, this within bracket thing, we have calculated here. So it's h theta x of I after some mathematical manipulation minus yi into xj of I. Okay, if you, because it's a log function, easy, we can easily differentiable. So this particular thing is this. Okay, so that we calculate. So now our gradient descent algorithm is what? Just say j theta, sorry, j theta j minus alpha of initially what we say that d del theta j of g of theta, g of theta. Now this g of theta is what? This g of theta is basically what? G of theta is that, what is this? That we said earlier, that 1 by m is equal to 1 to m xh x theta xhi. This is same thing. Okay. Bracket x theta j xj. That is, so we put it here, and that is alpha. It's alpha of this. That part we put, it's 1 by m and this particular thing. No, this 1 by m is not there. I think 1 by m is there. Somehow it is 1 by m. Okay, and algorithms look identical to linear regression. So for linear regression, h theta, only difference is that h theta is equal to, in linear regression, h theta is equal to theta transpose x. Logistic regression, this h theta x is equal to 1 by 1 plus d by theta transpose. But rest is same. Equation is same. Simultaneous update. Okay. So now we see that what is the optimization criteria for our gradient descent technique. So first one is step size. As we said earlier, too small, if the step size is too small, the convergence rate is slow and thus inefficient. If it is too large, it may not converge. So what I think you remember, that if it is a convex kind of thing, if it is too small, change the colors, you understand. This way, so it is a very slow. So when alpha is very small, and it is a slow and inefficient kind of. On the other hand, when it is a too big, so maybe it is here, it is go there, there, and kind of there, something. So may not, so it is may not converge kind of thing. Something like that. When alpha is very large. So we have to take alpha. And another thing can get stuck on the flat area as a function, and it is easily trapped in local minimum. These are some problems with this gradient descent that I mentioned. Now we use that some thing about gradient descent. Gradient descent is a popular optimization technique, machine learning, as you all know, and it can be with the most, if not all, the machine learning. It is used very, it is very popular, you can say. Okay. The gradient is the slope of the function. That you know what is a gradient. It measures the degree of change of a variable in response to the change of another variable. Now, what is important here that theta j is going to change when as alpha into delta of del theta j of j theta. So that is somewhat gradient descent. This kind of weight updation algorithm. It's weight updated in this way. So it's the gradient is a slope. So this is a slope. Now what is theta j? Theta j is basically, so it is a, you can say this part, this particular thing is what is a noise gradient. Okay. So this noise gradient is multiplied with this learning rate, and then this part is basically depending on this slope, positive or negative, is added or subtracted from the corresponding theta. So a gradient is a slope function. It measures the degree of change. So that is the change is this change of variable in response to changes in another variable. So there is a change in this variable and it influences another variable. Mathematically, gradient is a convex function whose output is the partial derivative of a set of parameters of its input. The greater the gradient, the steeper the slope. That you understand very easily. So that if it is a here, so its slope is more steeper. If it is there, that is basically idea. Starting from the initial value, gradient descent is run iteratively to find the optimal values of the parameters, to find the minimum positive value. So what we basically do, if we start here, we can start, we can close it. This is the gradient descent. Minimum possible value of the given cost function. We already grammatically or geometrically we have shown this how actually gradient descent converge. So there is a different types of gradient descent. It's a batch gradient descent, mainly what we have used, and there is a stochastic gradient descent, and mini match is the intermediate things. So these three are most common gradient descent used. So now, so what is stochastic gradient descent? See, this is also a very important part. The word stochastic means a system or process that linked with a random probability. Okay. Now you see in this gradient descent where exactly this formulation is there. Now it is when every step we calculate this function for every samples. Okay. So every samples, if m is very high, so number of training sample is very high. For every training sample, each iteration of gradient descent depend on the each training sample. If h is, let's say, 10,000 or 1 lakh, so every samples we have to take into consideration to do the one step or one iteration of the gradient descent. That is computationally bit expensive. So one in this case of random, hence in stochastic gradient descent, a few samples are selected randomly. Instead of few samples, we say it may be one randomly instead of the whole data set of the each iteration. So this whole data set M is not, rather than if you say In case of M, let's say few, or let's say for case a single sample. In gradient descent, there is a term called batch, which denotes the total number of samples from a data set that is used for calculating the gradient of each iteration. So if batch size is very high, so definitely M is very high. Okay. So normal gradient descent, that is the computationally expensive. In a typical gradient descent optimization like batch gradient descent, the batch is taken to be the whole data set. That's what it is said. Although using the whole dataset is really useful for getting the minima in a less noisy and less random manner, but the problem arises when the dataset gets big. So definitely, these gradient descent we should consider all from the mathematical point of view, because that's why if what actually we are doing, if I don't know, you remember this. This is the contour, and gradient descent means what? You are here sometimes. Now you can get there. You can get here, you can get there, and something like that get comes in. So some kind of thing. Okay, so but this thing is smooth kind of thing if we use consider that all this. Okay. Minimum less noisy, so this is a very or less random manner, so this is a more or not random. But suppose you have a million samples in your data set. So if you use a typical gradient descent optimization technique, we'll have to use all the 1 million samples for completing one iteration while performing the gradient descent. And it has been done every iteration until the minima is reached. Hence, it becomes computationally very expensive. That's what I say. That is the, it is computationally expensive. Expensive. It is computationally expensive. So what we generally do in case of stochastic gradient descent, this problem solved with a stochastic SGT, stochastic gradient descent. Only single sample, the total batch size one to perform the each iteration. Or we randomly choose, we choose one randomly. The sample is randomly shuffled and the selected performing the iteration. Okay, so here you can say this is the normal gradient descent. What we do? This is this particular things is there. You can say, but here you can say that this is change I in range of m alpha of yi minus yi into x with single sample, randomly picked, randomly picked. So that is the difference. So here you can say all samples we are taking, we are a single sample. There is no summation done here. Okay. So in stochastic gradient, we find out the gradient of the cost function of a single example at each iteration instead of sum of the gradient of the cost function of our example, less expensive than normal gradient descent. Definitely, only one sample. Since only one sample data set is chosen random for the each iteration, path taken the algorithm such minima is usually noisier. Why noisier? Because the question now that the single sample you are taking, how well it represents the total distribution. If it is if it represents well, this is good. If it is not represent well, definitely is a single sample that is noisier. A typical gradient descent. But doesn't matter all the match because the path taken by the algorithm doesn't matter as long as we reach the minima and with the significance of the training time. So exactly what happened here. This is a typical, so this path is very smooth. The typical batch gradients. And here it is the basically the single sample, there's a lot of noise here, but you can, but it is slow. That is very fast, but random. So these are the actual on these contour plots and how actually these things. These are more noisy. path is random, noisy, or random in nature. Okay, so stop here today. Thank you for